Welcome to Brain Vision.
16.72. So we have two sinusoidal waves of the same frequency, which is 120 hertz, and amplitude. We're sending them down along the positive direction of an x-axis that's along a tensioned string. And so we can send them in phase or with various phase shifts. And here, this is shown in terms of a distance by which they're shifted. We can think of this as being in terms of, which point along the wavelength, except the wavelength is something we'll have to figure out from this. And so we want to find just sort of the wave parameters for one of the waves here. So first, for interpreting this figure, it's helpful to use this equation from the chapter that tells you the amplitude of a resultant wave as a function of the phase difference between two identical waves. So now for the amplitude of one of the waves, we can see if the distance of the phase shift is 0, that still corresponds to a 0 degree or radian or what have you phase shift. So y sub s prime is going to be twice the amplitude of one of these waves. We're told that the scale here is 6 millimeters, so this is 3 millimeters. Now for the wave number, when the shift distance is 10 centimeters, the amplitude of the resultant wave is 0. So at 10 centimeters, the cosine of half the phase difference has to be 0. So this implies there's a half cycle phase difference when they're 10 centimeters apart. This implies that lambda is going to be 20 centimeters. And so then we know that the wave number is 2 pi over lambda. Which means that the wave number is 31 radians per meter. Now for the angular frequency, we know that this is 2 pi f. We're told f is 120 hertz. So this is 754 radians per second. And now for the sign we want here, we're told in the statement of the problem that they're traveling in the positive direction of the x-axis. So we need a negative sign on the omega t term here to make that happen.